Hello! Today I'm going to prove to you Pythagoras' theorem. So firstly, what is Pythagoras' theorem? It's a relationship between the sides of a right angle triangle. So let's draw one out and we'll show you the relationship. So it doesn't matter what the side lengths are. This relationship will always be true as long as we have a right angle, which is an angle of 90 degrees within the triangle. So when we label the sides, we label the longest side C, and then the other two sides are A and B. Doesn't matter which one's A, which one's B, as long as they saddle the right angle and C is opposite the right angle. So the relationship, Pythagoras' theorem, states that A squared plus B squared is equal to C squared. So the sum of the squares of the two shorter sides is equal to the square of the longer side. You might sometimes see this written with the square root on this one, and this just being C on this side. And that's giving you then a formula for finding the longest side, given the two shorter sides. So the proof of this then is we're going to draw another right angle triangle, and we're going to then draw a few more afterwards, all identical, where they have been rotated by 90 degrees and stuck together to form a bigger square. So we can see here we've got like 4 squares along this one, this is 7 squares along. So if we draw another side length of 7, so 1, 2, 3, 4, 5, 6, 7, and another side length of 4, what we've done is we've drawn an image of our original triangle, where it's been rotated by 90 degrees and it's a similar triangle basically. It's exactly the same size, just been moved. It's not been stretched, not been scaled in any way. We can do that again. We can draw another 7 along here. That's 3, 6, 7, and another 4. Connect this one up, and then do the final part over here as well. Connecting those up, fill in our square. If we go around now and sort of label the angles as the right angles, label the sides. So this short one can be A, this long one would be B, and A, B, and A, B, and A. And all these ones in the middle are going to be C. Very nice. So the first thing we have to notice is when we were drawing these, like to draw the image of the original triangle, we rotated everything by 90 degrees. So this C line has been rotated by 90 degrees as well. So the angle between the two is going to be 90. And this argument will follow for all the other triangles that were drawn. So all of these angles are 90 degrees. The next thing we can do then is to consider the areas of these triangles and these squares basically. So if we think about the large square, the area of that large square, well, the side length is going to be all the way along here is A plus B. So the area of that large square is going to be A plus B all squared. And that's going to be equal then to the area of all the composite shapes inside, all the shapes that make up this larger square. So we think about these 4 triangles and this one square in the centre. So the square in the centre has a side length of C. So the area of that square is going to be C squared. And then we have to add on the 4 areas of the triangle. And an area of a triangle is half times base times height. So we'll have to add on 4 lots of a half times the base of B times the height of A. So that can be A times B. If we expand everything out now, the left-hand side gives us A squared plus 2AB plus B squared. The right-hand side with the C squared is still there. And we expand this out, the 4 times the half gives us 2. So we have 2AB. The next thing to notice then is this 2AB and this 2AB are both positive on both sides. So we can cancel them off. We can subtract 2AB from both sides and they'll be eliminated. That will leave us then with on the left-hand side A squared plus B squared. And on the right-hand side, just C squared by itself. So we've proved the formula. We've proved Pythagoras' theorem, which is beautiful.